Welcome to 6.2 in our continued discussion on fields for low orbits as well. And when we talk about orbits, it's no surprise that we must talk a little bit about a satellite, which is an object that revolves around another object due to the force of gravity. Being experienced. We should know that all planets are natural satellites of a star, such as the Sun. And all moons are natural satellites of planets. So those are natural satellites, planets and moons. Okay, communication satellites are clearly artificial satellites, since they have been artificially or physically placed into orbit. We have physically placed them into orbit around the planet. So let's, for example, take an object. Which is in the gravitational field of another object. Unfortunately, I have lost my red marker, so I'm switching possibly to orange and hoping for the best. If we take an object that is in the gravitational field of another object, what do we know about the net force that is acting on that object? Well, what we know is that the net is therefore equal to the force of attraction that is experienced by the two objects. For an object that is orbiting another object, what do we know about the net force there? Way back from Unit 1, we know that the net force will therefore be equal to the centripetal force. Well, we have the net force for both of these objects. What this tells us is the following. For an object orbiting another object, due to its gravitational field, we can conclude that the centripetal force is equal to our force of attraction, Fg. Recall from Unit 1 that Fc, our centripetal force, is mv squared over r, while our Fg will be g sorry, let me cross that out, mv squared over r will be g m1 m2 all over r squared. And we're also going to say that this m is our object that's orbiting, that's mass 1. So we have common factors, m1 on both sides. We can cancel those out. Canceling out common factors gives us an equation for orbital speed. And that gives us that v will be equal to the square root of g, we're going to let this m2 be the capital M in this case, all over r. And m is the mass of the object being orbited. G is our gravitational constant from yesterday's lesson. And r is the distance between the centers of the objects. And really, when we're given these types of questions, they're pretty straightforward to answer. If we're given a question that asks us to, let's say, determine the orbital speed and period of Mars as it moves about the Sun. And it gives us that the mean radius is 2.28 times 10 to the 11 meters, and the mass of the Sun is 1.99 times 10 to the 30 kilograms. So everything that we need is given to us directly in that question. Our radius r, the distance between the two, is 2.28 times 10 to the 11 meters. We're given the mass of the Sun because that's what Mars is orbiting, and that is 1.99 times 10 to the 30 kilograms. And our gravitational constant from yesterday, 6.67 times 10 to the negative 11. So we're asked to calculate the orbital speed v. So we'll be taking the square root of gm all over r. And that is simply a substitution directly into the equation. So I have my 6.67 times 10 to the negative 11. I have my 1.99 times 10 to the 30. All of that will be divided by my radius r of 2.28 times 10 to the 11. And that gives us a orbital speed of 24,128.04. So therefore, to correct significant digits, 2.41 times 10 to the 4 meters per second. And we're asked to calculate the period in this case as well. To calculate the period when we have an orbit occurring, we know that the orbit is in a circle, which is, then the circumference of the circle is 2 pi r. So we'll take 2 pi r for the distance that it must travel, and we'll take that over the speed, orbital speed given that we calculated above. So that would be 2 with 3.14 with 2.28 times 10 to the 11, and all of that will be divided by 24,128.04. And that gives us 59,000 59,343,404.67. And that is my period. So that'll be 5.93 times 10 to the 7, and that will be in minutes. Which, just as an FYI, this answer here is approximately 41,210 days for this to occur. And that's quite a long time. And that's how long it takes Mars to orbit the Sun. One orbit around the Sun is that 41,210.